Okay, so our next speaker is Sean Griffin. He'll be talking about tournaments and slide rules. Please go ahead.
Thank you. Thanks for the invitation. Or sorry, thank you for the introduction. Thank you for the organizers for having me. It's nice to do an in-person talk and be able to see all of you. So I'm going to be talking about some combinatorial formulas coming from geometry. I'd like to start with the combinatorics, and then at the end, I'll tell you a little bit about the geometric motivation. And the title might be a little bit deceiving because the tournaments I'm going to be talking about probably aren't the tournaments you're thinking of, and the slide rules probably aren't the ones you're thinking about either. I'm not going to be computing any logarithms by hand in this talk. And this is joint work with Maria Gillespie and Jake Levinson. So first, let me tell you about asymmetric multinomial coefficients. So we all know and love the multinomial coefficients. And these have a really nice recursion where you subtract one from each of the parts. And Cavalieri, Gillespie, and Monin introduced the asymmetric multinomial coefficients defined by a similar recursion. So you fix a composition of n, and let I of k be the index of the rightmost zero. If there are no zeros in the composition, then you let I of k be 0. And for each index greater than I, you define a new composition with the following process. So you subtract 1 from the jth part, and then you delete whatever the rightmost 0 is of the result. So there are two cases. If kj is 1, then you delete kj. And if kj is greater than 1, then you subtract 1 from kj and delete whatever, and then you delete the ith position. So here's an example down here with n equals 10. So I of k is 5, the position of the rightmost 0. And the red is j equals 8. Since that entry is 1, we would delete that entry because we subtract 1 from it and then delete the rightmost 0. For j equals 9, well, that's a 3, so that's greater than 1. So we would subtract 1 from it to get 2, and then we would delete the rightmost 0 in the 5th position. So how does the recursion work? There's the definition again of kj, and the recursion defining these asymmetric multinomial coefficients is called the asymmetric string recursion, where you sum over these kj tildes. And here's an example down here. So for the first step, you would essentially delete this 1 in the 3rd position. And I'll talk more about this later, but Cavalieri, Gillespie, and Monin, their motivation was to compute the multi-degrees of a certain embedding of a moduli space into a product of projective spaces, or you can compute it in terms of what are called omega classes. They also gave a combinatorial interpretation for these numbers. So they give a condition for when they're non-zero. This is when the sum of the last I entries is at least I. And in that case, you can turn it into a deep path by having ki many labels in the ith column. This is maybe reversed left to right from how people usually draw deep paths. And they gave these combinatorial objects called column restricted parking functions. I'm not going to define. They're a subset of parking functions that count these asymmetric multinomial coefficients. And they also proved that if you sum over all of these coefficients, you get this really nice, beautiful formula, 2n-1 double factorial. Their proof was in terms of like an insertion algorithm in terms of the parking functions. So what I'd like to tell you about is 2 new combinatorial interpretations of these numbers. And parking functions are great. I think we love them in this community. But what we wanted to do was to find something a little bit more geometrically motivated that matches the geometry of this moduli space, which I haven't defined yet. And I'll talk more about this, but there are special points in the moduli space that are indexed by trivalent trees. So leaf labeled trees where every internal vertex has degree 3. And we give 2 new formulas. one is called lazy tournaments, which is an algorithm of taking trivalent trees and partitioning it up into subsets that count these coefficients. And the other algorithm is we call slides, which allows you to directly generate a set of trees that count these coefficients. And you get different sets of trees in either case. And they come from two different geometric motivations. So first, lazy tournaments. For notational reasons, we're going to throw in 3 extra points, ABC, and order the ABC and 1 through n in this way. And given a trivalent tree, so that A and B are adjacent, which by adjacent, I just mean that the edges of A and B share a vertex. We'll define what's called a lazy tournament, which is generated by this tree. So by tournament, what I mean is that we kind of think of 1 through n as players, and pairs of players are going to play a game, and some of them will advance to the next round. How does this work? So we find the pair of, so first of all, we turn the leaf labels into edge labels. So I just transferred them to the edges, and then we find the pair with the largest smaller element. So A and B are adjacent, C and 1 are adjacent, but 2 and 3 are the ones that are adjacent with the larger, smaller label 2. And you can kind of think of 1 through n as ranking the players, and we say that the larger label automatically wins that round because they're more experienced. But in this tournament, in this lazy tournament, there's this funny rule where 3, the winner, may not be the person that advances. It advances most of the time, except in the case when 3 sees that 2 will be beaten by the person in the next round. So 3 sees that 2 would match up against 4, and 2 would lose against 4. So 3 is lazy and drops out of the tournament and allows 2 to advance. And then we find the pair with the largest, smaller label. That's 4 and 2. 4 automatically wins. And here, 4 doesn't see anything in the next round yet. So it advances. Then C and 1 face off because C is the largest, smaller label. And 1 sees that C will be beaten by 4. So C advances, 4 and C face off, 4 wins, and then 4 advances. So that's the lazy tournament of a trivalent tree. And what we proved is that this asymmetric multinomial coefficient is the number of trivalent trees with A and B adjacent, so that each label I wins exactly ki many times in the tournament. And the proof just uses the asymmetric string recursion and these forgetting maps that are geometrically motivated. It's the forgetting map is like you forget the label I and then contract some edges to get a smaller trivalent tree. And that's essentially how Cavalieri, Gillespie, and Monin, or they use those maps in order to prove the recursion. And as an easy, yeah.
So could you go back? I'm a bit confused about the definition. So A and B are also adjacent. So why don't they move forward? Or in general, if there are multiple I plus 1s which are adjacent?
Yeah, it just happens that since A and B are their smallest, then they never actually play a game.
Okay.
It's kind of, we could have just kind of erased B and left A and played the whole tournament, or just said maybe that's a root, but we wanted trees with n+3 vertices to match the geometry.
But just if I may ask a follow-up question, if I have many I plus 1, JJ plus 1, which face off, I understand that the first pair that faces off is the largest, smallest label. But what happens to the others? They don't face off, or they?
Well, you do it in succession. So everybody plays a game eventually, but they have to wait their turn until they're part of a pair.
Oh, I see. So starting point is with this smallest.
Yeah. So and then they have to play the games in succession. Yeah. As an easy corollary, we just get the 2n-1 double factorial formula because this is saying that the sum of the coefficients is the number of trivalent trees with A and B adjacent, and that's pretty easy to, yes. Yeah. I think you mean like get to the final round. Oh, I mean like in each round, it's not the winner of the tournament. It's like 4 wins 2 of its rounds. And 3 wins 1 round, 1 wins 1 round. So that's giving you the the composition. So we essentially get the 2n-1 double factorial formula for free by counting these trees. The other interpretation in terms of this algorithm called sliding. So instead you start with your composition and you start with the tree on A, B, and C. And then in each step you insert the label I and perform a bunch of an operation called sliding at I. So after you insert I, say this is the vertex where I is inserted, the tree gets broken up into these different branches. One of the branches will contain A, which is special, and then you look for the smallest label that's not in the A branch. And then you slide the minimal branch towards A and creating a new edge. And then at the end of that process, you're allowed to distribute the remaining branches however you want to. So for example, this yellow branch could move over to the new vertex created, or the yellow and green could swap, but you couldn't put both green and yellow on the M vertex because that just wouldn't be allowed because of degree reasons. So at the end of this process of doing these slides, you get a set of trees called the slide trees. And here's an example. For 102, we insert 1, and then B is the smallest label, not in the A branch. So that slides over towards A, and you get the single tree. And then this is saying insert 2 and do 0, 2 slides, and then insert 3 and do 2, 3 slides. So you insert 2 and 3 and then perform 2, 3 slides. Here are all the ways to insert 2 and 3. And some of them, when you do the slides, some of them will result in trivalent trees. Those are the ones you take. So the first one, this first one will result in a single tree. In general, it could be a whole set of trees, but in this case, just 1 tree. And then last tree results in a single trivalent tree. And the theorem is that the coefficient is the number of slide trees. And actually, our proof of this theorem is completely geometric. It's totally different, completely geometric. We have no idea why these trees satisfy the recursion, and we have no bijection between these slide trees and the tournaments. So now let me tell you a little bit about the geometry underlying this. A moduli space is roughly a space that parametrizes geometric objects. So a Grassmannian is an example of that. Every point in the space corresponds to a K-plane. And the moduli space that I'm working with here is called the moduli space of genus 0 stable curves with n marked points. Essentially, one of the points, the interior of this moduli space is all ways of labeling the projective line with n points, n distinct points. Here, unlike in the morning talk, when I draw a circle, I'm not drawing it as a disk. It's just a representation of the projective line and points on it. And then what happens when you take limits in this moduli space? Well, say 3, 4, and 6 all start approaching each other. What's the limit point? Well, in the limit, essentially what happens is 3, 4, and 6, before they collide, they don't actually collide, they go and form their own component. So this little circle down here represents an entirely new projective line component that intersects the original one. And then maybe 1 and 5 want to collide, and then they have to bubble off into their own component. So those are the points in the moduli space. And for each of these stable curves, points in the moduli space, we can give it a combinatorial type in terms of a trivalent, or in terms of a tree, labeled tree. So the vertices are the components and the marked points. And given two components that intersect, we draw an edge between their vertices. And we also draw edges between the marked points and their components. So these are the dual trees associated to the three stable curves. And the combinatorial condition here is that a dual tree is defined to be one where each internal vertex has degree at least 3. So you can use this to stratify the space, sort of like the Schubert stratification of the Grassmannian. So XT circ is the set of all stable trees with dual tree T, and then you can take its closure to get a closed stratum. And there's a nice formula for the dimension of a stratum, just in terms of the excess degrees at the internal vertices. And in particular, this dimension formula tells you that the dual tree is a trivalent tree if and only if the stratum is a single point. So here is a trivalent tree, and it corresponds to some zero-dimensional boundary stratum. And whereas on the right, that tree represents a curve, a whole curve in the moduli space. Maybe I'll skip most of this due to time, but essentially there are these distinguished Chow classes or cohomology classes for each label, for each marked point called psi I. So this A star is the Chow ring where every subvariety has a representative class. And we have these distinguished Chow classes called psi I. And the upshot is that from these classes, we get a map to projective space called the Kapranov map. So we get different maps to projective space. And the psi I class is what you get by taking a hyperplane in the projective space and taking its inverse image under the map. And you can also, down here, I drew a picture of how you could compute this map in coordinates. So it can be very hands-on. And now you can use this map to get an embedding of your moduli space into a smaller moduli space crossed with projective space. So in the first coordinate, you can use your forgetting map, which forgets the largest marked point. And in the second coordinate, you have the Kapranov map, which sends it to projective space. And if you keep iterating this process, you can get an embedding of your moduli space into a product of projective spaces. And we define, so we call this the omega or Kapranov embedding, and then the omega classes are essentially the inverse images of hyperplanes from each of the projective space coordinates. And essentially what happens is that you can compute, these asymmetric multinomial coefficients can be computed in terms of these omega classes. So originally, it was already known that if you multiply psi classes, you get a multinomial coefficient times a point, the class of a point. And just as a side to connect it to an earlier talk by Benjamin Solomon, this is kind of a genus 0 slice of intersection products in higher genus. And you can throw all of that information into a generating function and get a solution to the KdV equation. So there's some connections with physics here. And on the other hand, Cavalieri, Gillespie, and Monin proved that if you intersect omega classes, you get these asymmetric multinomial coefficients, and that's what they were trying to compute. So to kind of summarize the last few slides, the asymmetric coefficients can be computed in terms of these omega products, and those can be computed explicitly in terms of intersecting hyperplanes in the moduli space. And the question we wanted to answer was, can you actually compute these coefficients by doing the intersections explicitly? if you try to do it with generic hyperplanes, well, it's hard to come up with like a combinatorial meaning for what are those points. But instead, what we did was we intersected moving hyperplanes. So we intersected these hyperplanes with parameters, t parameters. And if you allow the t's to be generic enough, you'll get intersection points in the interior. And as you take a limit, as all of those parameters go to 0, you have to do it in a certain order. You get boundary points, which is something that has a combinatorial interpretation in terms of trivalent trees. And if you choose these particular hyperplanes and do this limiting intersection in the moduli space, you get exactly the slide trees. So that's where our slide trees formula came from. So the proof is completely geometric. And even better, you can do this in higher degrees. So if you intersect fewer than n omega classes, what you get is a sum of boundary strata. And we did it in such a way that you actually get a positive multiplicity-free sum of boundary strata. So unlike with Schubert classes, these boundary strata classes, they don't form a basis, they have some relations. But we are able to find one such formula for these products that gives you a positive multiplicity-free sum. And essentially what you have to do combinatorially is stop the sliding algorithm at a certain point. Like if you do omega 1, omega 3, then you only do one slide and 1 3 slide. You don't do the extra 3 slide. And those are the 4 trees you get. And we can also do this for psi products as well. You can multiply any products of psi classes and get a positive multiplicity-free sum of boundary strata. And just to wrap up, we have some interesting connections to pattern avoidance, which I didn't mention during the talk. We can kind of partially describe these slide trees in terms of 2,3-1 patterns. So they're counted, there's a subset of the slide trees that are counted by Bell numbers, but we don't really know how that could extend to slide trees in general. It would be interesting. I think it would be really interesting to have a pattern avoidance criteria for more classes of slide trees. And this problem I already mentioned, can you find a bijection between slide trees and tournament trees? And there are all of these different generalizations of moduli spaces to homogeneous, to Hasse spaces, to stable maps, and they all have psi classes. So are there generalizations of those formulas to those settings? So thanks for listening.
Questions?
So maybe this is just a little superficial, but you had the moduli space and the circles made me think cactus group. Do you know how the cactus group acts on the lazy tournaments, or can you?
Actually, I don't know. We were mostly working with the complex geometry, and I think the cactus group has to do with the real geometry, if I'm remembering correctly. But that's a really interesting, yeah, that's a really good question.
Very nice talk. I was thinking, if you have a tree, can you say which compositions it will appear in the product for?
So it can appear at most. So if you're doing omega products, then it could appear at most once.
Right.
Sorry. Okay. For tournaments, there are no overlaps. So it could appear at most once as a tournament tree.
But I mean, could you?
But for slides, we're not sure. We're not sure how to tell. Yeah, so we have a condition in terms of, so if you take your tree, maybe this partially answers your question, which is we have a way of taking the tree and a composition and saying, is it possible to get this tree at the end? Well, there's some edge labeling that you can do to check whether that's true without having to go through the algorithm.
Oh yeah, there is one question from the chat.
Oh, can
Well,
I,
then
can anyone see it?
it was answered by the collaborator.
Okay. Thank you, Maria or Jake.
Okay, if there are no more questions, then let's thank Sean again.